Hi my scholars, this is my school channel and my name is Abiola. For this video lesson, we'll be solving the JAMB CBT past question for the subject physics. For the year 2010, do not go anywhere, stay with us and we'll be right back. You're welcome back to my school YouTube channel. Right there, we are going to solve question 36 to 49. So let's start with question 36, okay, till we get to question 49. So we have the diagram above represents balls in an undulating surface. All right, so which of the following option represents position of stable equilibrium? So when we refer to equilibrium, we have three types. We have the stable, we have the unstable, and we have the neutral. So for the stable, once the object is slightly displaced, okay, it returns back to its original position. For unstable, after the slight displacement, it goes further away from its original position. Then for neutral, a new position will be gotten or will be made, okay, after the slight displacement. So using those concepts now, we are going to see that the positions that represent equilibrium, they are III, VI, and IX. Okay, so let's see the option that has these combinations. So we have III, we have VI, then we have IX. So the correct option here is option C as the valid one. Number 37. A bulb of weight 0.1 Newton hangs from a massless string of length 50 centimeter. Now, a variable horizontal force which increases from 0 is applied to pull the bulb until the string makes an angle of 60 degrees with the vertical. So the work done is what? So right here, we can just pull up a diagram. So this is a frictionless pivot, right? So we are told that the string is unstretchable and massless. All right, so we know this. And we are told that this string makes an angle with the vertical, the amplitude, okay, at 60 degrees. Okay, so I have here at 60 degrees. So take note of what we are working on. So you can see that when we talk about weight, mass times gravity, so you know that the effect of gravity, we are looking at this direction, right? So either like this, or you are still looking at something that extends this way, okay, based on the oscillatory movement of the pendulum bump. So you may be talking about, probably like this or like this. Well, basically, we are looking at mass times gravity, and you know where gravity acts. So this will be mg cos theta. So if what we are required to do is to consider it towards the equilibrium position, okay, if it was coming to this back to rest, okay, that's where we are going to have sine theta. All right, we see that now. So very easy. So remember that work done equals to force times distance. Our distance at this point, remember, cos theta, right? This is our force. F, mass times gravity, or mass times acceleration due to gravity. So I have my work done equals, now remember that this bulb acts as the point mass, right? It's modeled as the point mass. So right here I have my force, okay, which is 0.1 times d, that is the length of the string, 50 centimeter, but we have to bring it to meter. So 50 centimeter is actually 0.5 meters. Okay, that's 50 divided by 100, that is 0.5 times cos 60. So I know that cos 60 is 0.5 also. So 0.5 times 0.5 times 0.1, I should have 0.025. Remember, work done, the unit is in joules. So let's see if we have 0.025. Okay, very well, we can find that in option D. So option D is the valid option. 38. Two metals P and Q of length L1 and L2 are heated through the same temperature difference. Okay, so if the ratio of the linear expansivity of P to Q is 2:3 and the ratio of the length is 3:4, okay, so what is the ratio of increase in length of P to Q. So this is what we are going to do. We are just going to use our idea of the concept of ratios. All right, so we are told that two metals, P and Q of length, L1 and L2. So we are talking about linear expansivity right here. And we record that linear expansivity, right, equals the increase in length, right, over the original length times change in temperature, okay? So right there from what we are told, we see that if the ratio of their, okay, yeah, we have two metals, P and Q of length, L1 and L2. So let me just indicate that P equals to L1, Q equals L2. All right, so are heated through the same temperature difference. So right there, I can hold their temperature values as constants. Okay, I can just take it out because it's going to negate one another. All right, we go further and we have if the ratio of their linear expansivity of P to Q. So linear expansivity of P to Q, you know, P to Q, you see the same thing as saying P ratio Q. You see the same thing as saying P over Q, right? Yes, so that is 2 ratio 3 or 2 over 3. That's for their linear expansivity. So let me call the linear expansivity of P as this and of Q as this. So we are having our values sorted out one after the other. Okay, then, and the ratio of length is 3 ratio 4. So length of P, you know, P is actually L1, the length, Q is L2. So L1 ratio L2, okay, it's still the same thing as L1 over L2, right? And that is, we have 3 ratio 4, right? 3 ratio 4 or 3 over 4. Simply put, that means L1 is 3, L2 is 4. All right, so let's use this formula. So remember I said that they actually utilize the same temperature. So we can see same temperature difference from the question. Very good. So that means I can remove temperature. So we are asked to find what is the ratio of increase in length? So increase in length, this is what we are looking for. So let me identify this as for linear expansivity of P, right? Okay, so we can see that. So let's cross multiply. All right, so that means increase in length, right, for P will be linear expansivity of P, right, times the length of P. So that means for the same thing applies to this. Increase in length for Q, that is linear expansivity of Q, right, times the original length of Q. Do we see that now? Okay, so and we are told that the ratio, so that is this over this, isn't it? That means delta L1 over delta L2, please. Okay, so that means this over this and this over this. So if I want to go further, that just implies that I can replace this with P and Q just to make it easier. Okay, P over Q equals, you can see that, or I can just maintain it this way depending on what you want us to work with. So either you have this, or let me just put it this way. Okay, let me stick with what I've been doing. Okay. All right. So what is the linear expansivity of P? We have 2. And see that times the length. We have 3 over. Let me write this. Okay, then we have linear expansivity of Q. We have 3 times length of Q. We have 4. Right, 3, 2 here 1, 2 here 2. So we can see that the ratio of their linear expansivity is 1 ratio 2. 1 ratio 2 or 1 over 2, right, or 1 to 2. Okay, so whichever one that is available. So let's go back to the screen to sort that out. So the ratio of increase in length of P to Q is 1 ratio 2. So option C is the correct option. Question 39. The velocity of sound in air at 16 degrees Celsius is 340 meters per second. So what will it be when the pressure is doubled and its temperature raised to 127 degrees Celsius? So I want us to know this. Okay, so it doesn't matter. The pressure of the surrounding air does not affect the speed of sound in air. Okay, so even though it's tripled or whatever, it doesn't count. So whatever value that is being assigned to pressure here is unnecessary for us. All right, so we should know that when it comes to velocity of sound in air, you know, you are looking at two factors. I can say the two major factors, at least for this context. We're talking about temperature, right? And we are talking about the medium. Okay, like for instance, you know, if you look at the temperature you have here, 16 degrees, you know, it's 340 meters per second. When it is at 0 degrees, around 332 meter per second. So when you talk about, you know, I've mentioned that the two factors that are key, especially in this context, they are temperature and medium. So let's consider medium. Like in air, you know, you have like 332 at 0 degrees Celsius, you know, but when it comes to water, it's around 1,500 meter per second. You know, it's still 5,000 meter per second. So you can see that what should affect velocity of sound, you are talking about temperature again, then medium, right? The sound is traveling through. All right, so also remember that sound do not travel in a vacuum. So let's go back to this, and the velocity of sound increases with temperature. So you can see at 0 it was 332, now at 16 it's 340. So let's solve this. So what will it be when the pressure is doubled and the temperature raised to 127 degrees Celsius? So whatever standard that we are working with should be in Kelvin for the temperature. So remember, this is what we have, square root of t, right? So for that scenario, that means we are looking at v equals k root t, isn't it? That is v over root t equals k. Then I can still go further to say v1 over root t1 equals to v2 over root t2. This is not volume, this is velocity or speed of sound in here. All right, so we are told that what will it be if it's temperature? What will be the velocity now if the temperature is raised to 127 degrees? Okay, so I have to bring the temperature to Kelvin scale. All right, so the first is 16. So 16 plus 273. Right, so that should give me 289 Kelvin. This is my T1. That's correct. Then my T2 is being raised to 127. So that is 127 plus 273 should give me 400 Kelvin. So this accounts for my T2. So basically we are asked to look for V2. So if I'm to make V2 the subject of the formula, that means V2 equals V1 times root T2, right, over root T1. So that should be V1 is given as 340 times root T2. What's T2? T2 is 400. So square root of 400 is 20. 20 times 20 give you 400. So this is times 20 over square root of T1, 289. So square root of 289 is 17. I know that. 17 here 1, 17 here 20. Okay, so 20 times 20 gives us 400. Okay, so meter per second. So we can see that this answers confirm the concept that the velocity of sound in air or the speed of sound in air, using our confirmation from the screen, should increase with temperature. So I mentioned earlier at 0 degrees is 332, at 16 this is 340, then at 127 it is 400. So don't forget that. So the correct option is option A for 400 meters per second. 40. 3 capacitors of capacitance, 2 microfarad, 4 microfarad, 8 microfarad are connected in parallel, and a PD potential difference of 6 volts is maintained across each capacitor. Now the total energy stored is what? All right, so we can use the formula. Remember that a capacitor is actually a device that you use to store electrical charges or electricity, basically. Okay, so looking at what we are given, now this arrangement is made in parallel. So do not confuse this with your regular ones that you know that, oh, okay, if resistors are arranged in parallel, it is 1 over R equals 1 over R1 plus R2 plus 1 over R2. No, that's not it. So for capacitors arranged in parallel, it's just going to look like your series of the other side. So for capacitors in parallel, it's going to just be total, I can say C total, right? Total capacitor, we just add up regularly. So that will be 2 plus 4 plus 6 plus 8 rather. That is 2 plus 4 plus 8, okay? Your microfarad, right? Microfarad. So this micro means 10 raised to the power minus 6. So this is 2 plus 4, that is 6 plus 8, this is 14. So I can say 14 times 10 raised to the power minus 6. All right, so for us to find out the total energy stored, okay, so you can use this formula, half, you can say half QV, or I can say half CV squared, depending on the parameters available. All right, so I have this, right? So that will be half times 14, right, times 10 raised to the power minus 6 times my V, okay, the voltage, of course, is the same thing. So that is 6 volts, you can see from the question, and the PD of 6 volts is maintained across each capacitor. So it's just 6. So 6 raised to the power 2, that is 6 times 6, isn't it? So right there I can say 2 year 1, 2 year 3. Okay, so let me just multiply these values. Then I should have, let me just multiply 3 times 6, 18, 18 times 14. Let's do that together, 18 times 14. This is not proportionality. So we have 4 times 8, I have 32, leave 3. 4 times 1, I have 4 plus this is 7. 1 times 8, I have 8. 1 times 1, I have 1. So 2, 7 plus 8. Okay, that accounts for 15. I leave 1. 1 plus 1, that is 2. So I have 252 times 10 raised to the power minus 6. Okay, I have 252 times 10 raised to the power minus 6. All right, so if I want to bring this to standard form properly, that should just be 1, 2. That is 2.52 times 10 raised to the power minus 6. Okay, remember the unit of energy in joules. So let's see if I have this available. All right, so I can find that in option C. So do not confuse this, because you know we have 252 times 10 raised to the power minus 6. All right, so if you want to bring the standard form properly, you know it's going to be dropped down by the 2 movement that we made, okay, to bring the decimal point to this spot. So the correct option is option C, 2.52 times 10 raised to the power minus 4 joules. Now it is possible for you to have a JAMB simulated experience. All you just need to do is to click on the link in the description below. It's going to take you to the Myschool website. Okay, right there you get to download the Myschool mobile app for your Android devices, or you can try downloading the Myschool software for your laptops and your computers. So join me as I solve question 41. A cell of EMF 12 volts and internal resistance 4 ohms is connected to an external resistor of resistance 2 ohms. Find the current flow. Remember that the EMF of a cell, you know, you're talking about the PD, okay, across its terminal when it is open, when that circuit is open, that is, it is not supplying any current to any external circuit. All right, so we are going to use this formula. Okay, so that is, the EMF is given as 12 over the external resistor, which is 2 ohms, plus the internal, which is 4 internal resistance. So that is 12 over 2 plus 4, that is 6, right? And that accounts for 2. Unit for current is ampere. So let's see if we have 2 amperes. Yeah, we can find that in option D. So option D is the right option. Please do not forget that you just have to hit that like button. Also click on the subscribe button and always tap on that bell notification so you can get alerts immediately we upload the next video content. 42. The diagram above shows a balanced meter bridge. Okay, the value of X is what? So we know that the meter bridge works on the principle of the Wheatstone bridge, okay, to measure an unknown resistance. So this is your R1, this is your R2, your L1 and L2. So we're just going to use the simple formula. Your R1 over R2 equals to L1 over L2. So I have R1 over R2 equals L1 over L2. All right, so let's just pull out our given data. Okay, so R1, we have two resistors, okay, they are arranged in parallel. So that will be, we have 8, 8, right? So that should be arrangement in parallel is 1 over R, right, equals 1 over 8 plus 1 over 8, right? That means 1 over R equals 1 over 8 plus 1 over 8, that is 2 over 8. If you find the LCM, this is 2 here 1, 2 here 4. So if I cross multiply, 4 comes here, R goes here. So that means my R equals 4. So R1 is 4 ohms, right? Then R2, we are giving R2 as 8 ohms, right? The next one there. Okay, so the L1 is given as X, then the L2, the remaining length, that's 100 minus X, centimeter. The length there is usually 100, okay? So let's impute these values. So I have R1, which is 4 over 8 equals L1 X over 100 minus X. So 4 here 1, 4 here 2, right? So basically I have 1 over 2 equals X over 100 minus X. So when we cross multiply, I should have 100 minus X, it's still the same thing, times 1 equals 2X. So if I collect like terms, right, I should have 100 equals 2X, right, plus X. Then 100 equals 3X. So dividing both sides by the coefficient of X, which is 3. So basically this should go, I know 3 can go in 10, 3 times, right? 3 can go in, remainder 1. 3 go in 10, 3 times remainder 1. 3 go in 10, that is 3, remainder 1. So that is 1 over 3. So that I have X equals 33.33333 centimeter. Right, so we know that L1 is 33.3 centimeter. L2 now will be 100 minus 33.3 centimeter, and that should be about maybe 66.7. Yeah, thereabout. So let's move back to the screen and see if we can tap out 33.3 centimeter. Yes, we can find that in option C. So option C is the valid option. Question 43. 3 4 ohms resistors connected in parallel have a potential difference of 16 volts applied across them. So what is the total current in this circuit? All right, so at first we have the arrangement of these resistors in parallel. So each one 4 ohms. So in parallel I have 1 over R total equals 1 over 4 plus 1 over 4 plus 1 over 4. So that should give me 1 over R equals, since the same denominator, right, that is 4. 1 plus 1, 2 plus, 1 plus 1, 2 plus 1, that is 3. So basically I have to cross multiply. That means I have 4 times 1 equals 3 times R. Yeah, so I have this. So basically the value for the total resistance should be 4 over 3 ohms. Right, so, and we should note this, that when it comes to arrangements in parallel, right, the PD across, okay, it's the same thing, but the currents differ for each resistor. So take note of that. So we have our V is given as what? Is given as 16. Wonderful. So remember that V equals IR, but right now we are looking for I. So what do? Divide both sides by R. So that implies that I equals V over R, or V divided by R, whichever one. So I can say my V is 16, right, divided by my R, which is 4 over 3. So that is 16 over 1 times 3 over 4. So 4 here 1, 4 here 4. 4 times 3, that is 12. So you can see we have 12 amperes. So let's see if we have that value presented right here. Yes, we can have that in option B. So option B is the accurate option. Please be informed that you can ask your questions right now. So how do you do this? Very simple. All you just need to do, click on the link in the description below. It's going to take you to the Myschool website. Right there you get to interact with our solution providers as you ask your questions right now. So join me as we solve question 44. In the diagram above, a 200 watt bulb is lighted by a 240 alternating current, okay, main supply. Now, if 1 kilowatt hour is sold at 40 naira, now the cost of keeping the bulb lighted for a day is what? So for a day, we know we are talking about 24 hours. So remember that energy equals power times time, right? So we have our energy consumed, right, equals power times time. Power there is 200 watts, right, times the time frame, which is 24 hours. So I should have 4800. All right, so that's for power. But remember that we are told that this bulb will be sustained for a day, that is 24 hours. So, and it's been sold for how much? It's been sold for per hour, it is sold for 40 naira. So that will be this times 40, right? Because this is how it works, okay? I can even break it down this way. You know, the energy consumed for a day, we talk about the power of the bulb, which is measured in watt, that is 200, right? Times the duration, which is 24 hours, right? Times the amount per hour, that is 40. Yeah, that's the same thing that we have there. So when we multiply this, so recall that we are talking about kilowatt hour, but this was given in watts. So it is salient that I actually bring this down to what? To kilowatts, and that is dividing by 1000, right? So I can still introduce it here, 1000. See the same thing that we are going to arrive at. So I have this struck out, right? I still have this struck out. So basically there's nothing at my denominator except 1. So I have 2 times 4, that is 8. 8 times 24, that should give us 192. So for a whole day, it should cost 192 naira if it is charged 40 naira per hour. So let's see if we have 192. Yes, we can find that in option B. So option B is the correct option. In case you have better steps or solutions you'd like to share with us, please, we are so much attentive. All you just need to do is to kindly use the comment section below, indicate that question number and the explanations you'd like to share. 45. In the diagram above, if the south poles of 2 magnet strokes steel bar, okay, now the polarities at T and V will respectively be what? Okay, so basically, you know, when you talk about methods of making magnets, you know, we can refer to the electrical method and the contact method. So the electrical method is considered as the best and the quickest. All right, so under the contact method, we have the single touch and the double touch. So this is a double touch that we're looking at right here. So the basic setup that we have, okay, in our materials, our common materials, this should be south as well, then north. Okay, so since this is south, the ending here, you know, this is a movement like this, like this to stroke. All right, so this is where it's going to end. This ending here, if this was south, this is going to be north. If this was north, this is going to be south. That's the regular setup that we have, that we know of. So south against north. But right here, we still have south, south. So working on that principle, all right, so if this is south, this is going to be north. If this is south, this is going to be north. So remember I said that it's just going to be opposite of the stroking pole, okay, that comes towards it. So right here, this is south, right, this is going to be north. This is south, this is going to be north. If this was north, right, this is going to be south. If this was north, it's going to be south. Why? We have south, south. So it's going to be north, north. So the correct option that we have here is option C for north and north. 46. In Faraday's law of electrolysis, okay, a graph of the mass deposited against the quantity of electricity is plotted. Now, the slope of the graph gives what? So, you know, when you just even take up this formula, right? Mass is proportional to the electricity. Okay, so we're talking about that's measured in coulombs. All right, so, and that is Q equals to IT. You know, at the end of the day, you have M equals to ZIT. That Z is the constant of proportionality for each element, and you can refer to it as the electrochemical equivalent. So option B is the right option. 47. The process whereby a substance changes from a solid to liquid when heat is applied is called melting or fusion. All right, so evaporation is actually from liquid to vapor below the boiling point. All right, so vaporization now is, of course, when it is applied, okay, yeah, when it is applied, okay, so what happens there is actually from liquid to gas. All right, then fission, probably we'll be talking about nuclear fission, breaking things, a bigger atom to smaller ones. Okay, so the correct option is option D for fusion or melting. Question number 48. An object is weighed at different locations on the earth. Okay, so what will be the right observation? Okay, so we should know that the comparison here basically is between mass, okay, and weight. So mass is defined as a quantity of matter a body contains. All right, and it is constant everywhere, even outside. I'm talking about the space. All right, while weight, you're talking about Earth's gravitational pull on the body towards its own center. So in that case, we should also know that this in turn influences acceleration due to gravity of a particular body. Okay, acceleration of an object. Okay, so there we are not talking about, we talk about weight, we are talking about its influence on acceleration due to gravity. And this varies from place to place. All right, it is minimum at the equators and it is maximum at the poles. All right, so in that context, we can say that the mass is constant even outside there, but the weight will vary. So option C is the correct option. Number 49. The radioisotope, we have uranium, atomic number 92, atomic mass 235, decays by emitting 2 alpha particles, 3 beta particles, and a gamma ray. Now, what is the mass and atomic number of the resulting element? All right, so we have uranium. So we are told that there are emissions, right? We have 2 alpha particles. Alpha particles, we are talking about helium. So 2 of it, okay, 2 alpha particles, that will be 2 times, okay, so we have helium 4 and 2, right? Then we have electron, for beta particles, electron. So we have 0 and minus 1, that is 3 of it. Then remember that the mass for the gamma ray is negligible, right? It's an electromagnetic wave, so that is actually gone. So we have this. So we have 2, 3, 5, right? Then we have 92. Okay, so it's minus everything that we have here. These are the emissions, right? So I should have this. Let me just have it like this, 2, 3, 5, 92. Okay, so I have minus, open your bracket, 2 times 4, that is 8, then 2, are we saying that? Okay, it's added to, then I have 3 times 0, that is 0, right? 3 times minus 1, that is minus 3, okay, so we can, 2 times 2, that is 4, rather, please, let's take note of that. So I should have 2, 3, 5, you can see that I actually skipped the symbols of elements because I'm looking at, okay, let's form a new unknown element, right? So I have 4 plus minus 3, that is 1, right? So I have minus 1 underneath. So I have 8 plus 0, I have 8. So 92 minus 1, that should give me 91, right? So I have 235 minus 8. Okay, that should give me 227. So for the unknown elements, let me just represent it with the symbol PA, right? Just though I'm looking at the atomic mass, okay, it doesn't fit for PA, for the elements with the symbol PA. All right, so the new atomic number and atomic mass should be 91 and 27, okay, or 27 and 91 for atomic mass and atomic number respectively. So let's see if we can fetch that out. So look at the order. What is the mass? Okay, atomic mass and atomic number. So atomic mass first, that is 227, then atomic number 91. So option C is the right option. We've come to the end of this wonderful video lesson. We believe you enjoyed it. Please do not forget that you have to hit the like button. Also click on that subscribe button and always tap on bell notification for you to get alert immediately we upload the next video lesson.